S-wave component in overdoped high TC cooperation.
Okay, you can put in the full screen model.
Yes, this is full screen model in my computer.
Okay, there is no problem. We can see.
Very well.
Maybe it's a problem.
So let me remind that there are different types of symmetries of superconductor gap. The upper one here is a S-wave gap, when gap doesn't depend on the wave number at all.
Professor, sorry to worry you too much. Maybe when you share, you are sharing only one file. Better you share the full screen. What I mean is the full files. Okay, because we see only your PPT. Yeah. When you share, try to share the full.
I share my screen.
The full computer, much better.
Yeah, this is the full computer, different files.
Yes, the full computer. Because if you share only the presentation, sometimes does not appear the screen. Okay. Oh, finally. Yes. Okay. Go ahead, please.
Okay.
Yeah.
Different symmetries of the superconductor gap. The upper one is the S wave. It doesn't depend on the wave number at all. The low one is D wave, a very well known D wave, operates when the gap is determined by different degree, that is nodal direction in the Brillouin zone. Well, nevertheless, extended S wave, S star wave symmetry also is possible. That is given by sum of cosines, cosine ky and cosine kx. It has different S not D wave, more complicated symmetry of the gap was found for heavily overdoped Visco 2212. It is shown in the lower part of my picture. And point A, this is Brillouin zone here. Point A, it is exactly the nodal direction. Diagonal direction is in Brillouin zone. You can see here maximum, not minimum. For D-wave gap, we should have a zero gap. But for this material with strongly overdoped cuprate, we see the maximum, not minimum. So it is the first example of the S-wave gap, extended S-wave gap. It was published 20 years ago. This is a reference here in the down of the picture. Well, there are some more evidence, experimental evidences for the unusual S-wave gap. For example, here this is RPS spectra for the same crystal E3123, E3123. The left one when electric field is along X direction, and in the right figure for y direction. We can see the difference of the spectra. It means that there is an anisotropy between wave number along x and y axis. Well, also in the Raman scattering, it was found that softening and broadening of the spectra are different in x direction and y direction for strongly overdoped rays. To understand this anisotropy of the gap, we doing electronic structure calculations for lanthan 2 copper 04 for different doping. And it is well-known problem that the material is strongly correlated. So standard LDA or density functional theory calculations are not valid because of the strong electron correlation. So many years ago, my group has developed the generalized time binding method to calculate electronic structure with strong electron correlation. So idea is the following. This is lanthan 2 copper 04 structure, and one copper 06 cluster is a unit. We consider it is a unit cell of our lattice. And what we are doing on the first step, we take all atomic orbitals of important orbitals for dx square minus y square and dz square, two orbitals for copper and 3 orbitals for oxygen, x, y, and z oriented p orbitals. So all these orbitals are shown in the right picture below, and overlapping of these orbitals. So what we are doing, it is exact diagonalization of this cluster, including Coulomb interaction on copper, Coulomb interaction on oxygen, and between copper and oxygen. So when we have done this exact diagonalization, we obtain a set of different multi-electron states. For example, vacuum state shown here with 0 hole. This is a state corresponding G10 P6 configuration. So no holes on oxygen, no holes on copper. The next states are single hole states. It is a mixture of hole on oxygen and hole on copper, like for undoped copper O2 or 4. Well, if you want to make a hole doping, you substituted lanthan by strontium. So 2 hole states appears. This is shown here. There are singlets and triplets. The lowest one is well-known Jankrai singlet. But there are a lot of different states, triplets and excited states also. So we can very quickly come back to the Hubbard model if you choose only the low state for 0 hole, 1 hole, and 2 hole. Then we immediately will obtain the states that are present in the Hubbard model. But what we're doing, we want to take all these excited states, and this is a set of orthogonal Asian states. So with a set of orthogonal Asian states, we define the Hubbard operators in the standard definition like it was done in the original Hubbard papers. The difference is that in the Hubbard paper, he has 4 local states, spin up, spin down, 2 particles and 0 particles. But we have all this set that is included in the chemistry of the material. And nevertheless, it is also the matrices, not 4x4 matrices in the Hubbard original paper, but it's a large size of the matrix. Nevertheless, we can work with these matrices. What is more important, we can determine Fermi operator creation or annihilation process is a sum of different excitations. This excitation shown here. Or for example, if you have D9 configuration and electron created, you will have D10. So each arrow here show excitation from one multi-electron level to another multi-electron level, and difference in the number of electrons is 1. And all these excitations contributed in this sum for the Fermi. So this is a little bit different language how to work with the multi-electron systems with strong electron correlation. Nevertheless, with this language, we write down the Fermi operators as a linear combination of set of Hubbard operators, and finally, the initial multi-electron model is written exactly like the Hubbard model in the X operators. So the difference from the original Hubbard papers is only the matrix X of X operators. It is a large dimension matrix. Okay, then we come back to the 5-band PD model for cuprates. This term corresponds to D holes on the copper. Lambda is orbital, Lambda corresponds to 2 orbitals. For the copper, dx square minus y square and dz orbitals. Also 3 orbitals px, py, and pz for copper. Hopping between copper and oxygen, just like in tight bonding PD model, and also all Coulomb interaction inside the copper, Coulomb UD, Coulomb interaction inside the oxygen, UP, Coulomb interaction between copper and oxygen, between oxygen and oxygen, and finally the Hund exchange interaction inside the copper. So all these parameters have been calculated from ab initio LDA agent functions projected onto one-year functions. This is a reference here when you can find it in more detail. And then we want to study orthorhombic crystal with a difference in B and A axis shown here. We fixed this difference about 4%. This corresponds to strongly overdoped cuprate. So all parameters are given in this slide for the local energies in the table and hoppings. So these hoppings have been calculated obtained from the LDA calculation without electron correlation. So it's like to obtain tight bonding model parameters from LDA through one-year function approach. Well, then we would discuss superconductivity with magnetic mechanism of pairing. In the Hubbard, in the TJ models, there are a lot of previous papers and previous authors who study this problem. I would mention Anderson, RVB theory, 1987, Bashkaranzu, Anderson, also 1987. Then cluster DMFT theory by Meyer, by Lichtenstein, and so on. Kalapina was the guy who asked, what is a superconducting glue? A combination of static and dynamical contributions. Well, so, and many others. Particularly, I will use a formulation of Plakida, 1999. This is a Russian physicist who works with the Hubbard model, and he used X-operator perturbation theory. We will do the same, but not original Hubbard model, for our modified multi-orbital Hubbard model. well, maybe I will skip details because it's too much notations here. The idea is exactly as in the Hubbard model. The difference is the large number of different parameters in this model, but no principal difference. And also, what is principal? We have our orthorhombic symmetry in our crystal. So equation of motion for the Hubbard operator green functions are constructed from the Hubbard. It is more or less Garkov type equation. So the Dyson equation is shown here for the green function, renormalized green function. And to obtain this equation, we use projection technique of Moritz-Swansek formalism. That is was given in detail by Plakida in 2003. So, well, so we did not develop any new method. We just used his method only for the large size of the matrices because of it is not Hubbard model. It is PT model with oxygen and copper. So all these matrices are given here. And then equation for system of equations for D and S star wave components of the superconductor gap. So the total gap, delta over K, is given a combination of D wave gap, delta D, and extended S wave gap. And for this gap, we have a Garkov type equation. And this is superconducting energy epsilon. B is the gap function. And finally, this is not, all these preliminary formulas do not see any sense to discuss in detail. So what is important, finally, we get a system of equations for components of the superconducting gap. Two components, D component and SY component. And this is a system of equations. Due to orthorhombic distortion, exchange interaction in X direction and in Y direction are a little bit different. They are shown here. And then we separate this system of equations for D gap and S gap. And finally, we get this linear system of equations for different gaps and for different doping and for different temperatures. And here are the solution of this equation. The left is the D gap, symmetry gap. Delta D is a function of doping on the horizontal line, X, and the temperature, the line that is. Can you see my cursor when I move it? So this is temperature and concentration, and this huge shield shows the superconducting gap for different temperatures and different doping. Well, on the right part, this is S star symmetry gap. It has quite different doping dependence. It appears only for the large doping when concentration is more than 20%. Hello, do you hear me? Okay, I will continue. So with this, on the slide, I show the large gap, G wave, and smaller gap, S star gap. And the total gap given by a sum of D and SY gap is shown here. Of course, S star gap is smaller than the D wave gap, and it appears only for the large doping, around 25% of doping. And it exactly corresponds to the overdoped gap found in the overdoped cuprates. Well, here I show the evolution of the Fermi surface with doping. And for small concentration of holes, we have small pocket. Then the pocket becomes larger, and finally it crossed the boundary of the brilliant zone. And then this inner part has small spectral weight. This so-called pseudo gap effect. And finally, in the large doping, we have standard Fermi liquids, Fermi surface with only one surface, without any pseudo gap. The idea of pseudo gap is demonstrated below. For example, we have two surfaces with a minimal spectral weight and the maximal spectral weight. And on the right down picture, we show the ratio or the attitude of minimal spectral weight to the maximal spectral weight. We can see that it decreases with doping, and finally it goes to zero. So there is no small Fermi surface pocket. Only normal Fermi liquid surface survives in the large doping.
Excuse me, Professor. You have 5 minutes. You have 5 minutes more.
Okay, I will close very soon. So here we demonstrate how the Fermi surface depends and changes with doping. 21% it is more or less clever to the optimal doping, clear, and 24% more overdoped. There is not very strong difference, but just quantitative difference. For example, for 21%, we have, for both doping, we have a large external surface here and here. But the pseudo gap surface is larger for 21% and is smaller for 24%. And this is the structure of the Bogoliub quasi-particles shown here, and density of states. Of course, density of states has a maximum near the flat band, near pi0 point. The same for overdoped, very sharp peak in the density of states due to this flat band. Well, so I'm close to conclusion. What is the main result of our paper? We found unexpectedly large value of the S-wave component in the superconducting cap in the narrow range of hole concentration in the overdoped high TC cuprate with ortholombic distortion. Doping results in a increase of the depth of the small pit around the K point pi. The large value of the S-wave component is due to the presence of the shallow pocket around the point pi with a small spectral weight. A decrease in the depth of the inner electron pocket when doping is growing increases the number of states that make a significant contribution in the S-wave component and the magnitude of this contribution. So the contribution of the states increase precisely the S-wave component. That's all. Thank you for your attention.
Thank you, Professor. We have the opportunity to 2 questions.
Okay.
Any questions? If you don't have questions, George? No? Okay. If you have no question, let's thank the professor again. Thank you, Professor.
Thank you.
Congratulations for your excellent talk. Now we'll have another speaker, is Professor Mauro Doria from Universidade Federal University of Rio de Janeiro, Department of Physics. He'll talk for us about, I have no idea. The origin of the linear dielectric spectrum and topology. Mauro, you have 14 minutes, missing 5 minutes, I will show you. 45.
Good morning, everyone. Thank you for your presence. The name of the talk is The Origin of the Linear Direct Spectrum and Topology. I'd like to thank the organizer.
Mauro, your microphone is not running.
It is. Hello. Angel Bustamante, Fulgêncio Silva, Luis Valadares, Juan Gonzalez for organizing this event, which I know it takes a lot of work and dedication, so I'm very thankful. So let's see if I can. Okay, should be here. How do I move? Could you help me? That's the change over here. In the past, go forward. Well, my point here is just one point. I want to convince you that the topological insulators, okay, the basic theory is a set of equations which are basically belong to the same family of the equations used to describe type 2 superconductors, which was proposed long ago by because of money. Just happens that these equations you have to include spin somehow. Okay? And then with these new equations, you can describe the Dirac linear spectrum, the Rashba interaction, the topological properties of the states, and the magnetic monopole nature of the states. Okay? And all this follows not from a relativity invariant theory, but just by the Schrödinger kinetic energy. That's my point. It's interesting that the study of surface goes back long ago. I just picked up one slide here to give you a feeling of it. This is 1964 by Ginsburg, and he says that it's possible to have attraction between electrons in the surface, but not in the bulk.
Recording in progress.
Which means that surfaces can have different behavior. What do I do with this? Thank you. So the Dirac linear spectrum has been observed in, for instance, and it's just written there. Energy is proportional to the wave number k. Okay, you have a Fermi velocity, 10 to the 6 meters per second. This is was observed in the something like 20 years ago. And then people did a theory about it for graphene. They essentially explain as hopping from one lattice to the other. The hexagonal lattice can be decomposed into two triangular lattices, and hopping from one lattice A to B. Okay, if you go to the continuum, you get an equation that is sigma p, linear in momentum. Okay, and sigma are the Pauli matrices, but they really represent some kind of hopping from one lattice to the other. They don't represent spin. This is the so-called Dirac-Weil equation. This equation was proposed soon after the discovery of the Dirac equation. Okay, and it's able to describe right-handed quarks, left-handed quarks or particles, leptons, and so forth. Okay, in particle physics. Okay. However, I mean, these states in condensed matter, when you look more carefully, okay, you have to understand, I mean, the description in high energy. You have helicity, chirality, Weil states, Majorana. So helicity are states that have a defined angular momentum along the spin direction. I mean, chirality is some kind of equivalent to helicity, but it's relativistic invariant. Then you have the Weil fields, which satisfy these, which are chiral states, and you have the Majorana fermions, which are particles without charge. Okay. It turns out that the Weil Hamiltonian, so to speak, written like that, where sigma is spin and d is the momentum, okay, this equation does not exist. Okay, for the simple that angular momentum is a pseudo vector, so this is a pseudo, and it's not possible to exist this equation. However, a zero helicity state is possible, as shown below. Okay. Interestingly, the Weil equation was proposed before the discovery of graphene and all that stuff. This is where in 1998 by Abrikossov. Okay? And he was trying to explain the linear magnetoresistance of the silver chalcogenides. And that's the equation you see here. And these systems, these materials do not have that lattice symmetry of graphene. So a year after, Abrikossov wrote again about the graphite this time. And again, you see the linear Weil theory, okay, proposed to explain the linear magnetoresistance. Okay. So we have here the question. The Dirac linear spectrum, of course, is not a consequence of relativistic invariance. You don't have the time dilatation or space contraction inside the material. So it's not relativistic. And the Dirac spectrum cannot be just described by a special lattice symmetry as done for graphene, okay? As it is found in many, many systems. There is a huge list of systems that have linear magnetoresistance, and many are shown through ARPAs to have the Dirac spectrum. So what's the origin of the Dirac spectrum, okay? So now then we go to the topological insulators. What are the topological insulators? Are systems that are insulators, but the surface, they conduct. They conduct it in a special way with a spectrum, linear, okay, in momentum. And there are many examples. Bismuth telluride and selenide and so forth. They show the Dirac linear spectrum. They have what's so-called Rashba interaction, and they have a property that is, to my knowledge, is not still well discussed in the literature, which is the spin momentum locking. Okay, what's the spin momentum locking? Is the fact that the Fermi surface spin and momentum are perpendicular to each other. Okay, and what's the reason for that? Okay, so you have the linear Dirac spectrum and this condition. And this is a gateway for many applications in spintronics, because once you have spin perpendicular to momentum, you can do a lot of interesting things. It's worthwhile to see that the literature back, almost 15 years ago, for instance, they define spin helical Dirac transport regime. This field, people create words, they come and they disappear. This one, spin helical Dirac, but essentially it's saying that the spin is perpendicular momentum, as written here. Charge carriers that behave as massless relativistic particles with an intrinsic angular momentum spin locked to its translational momentum. Okay, so we propose that this is a fundamental new property in condensed matter physics. And also there are now many studies of spin Hall effect without an applied magnetic field. The particles display spin Hall effect, and that's because they have their own magnetic field. They behave as some kind of magnetic monopole in this surface of the topological insulators. Very surprisingly, some of these properties are found in high TC superconductors, as the work of Lanzara and co-workers using SARPs, which in this case is ARPs, with spin, measuring spin as well. Okay? And they find that in BISCO, you have spin momentum locking also observed, okay? Which is some remarkable thing whose meaning is still to be understood. So there's a whole new dictionary of words in this area of condensed matter physics, insulators, spin helical Dirac, spin momentum locking, SARPs, magnetic monopoles, spin orbit interaction, Rashba term, breaking of time reversal symmetry, backscattering, Dirac cone, wire equation, Berry phase, and so forth. Okay, now we go to theory, where I want to make my point here. You go back to 1957, and you look at the Abrikosov's paper that gave rise to vortex physics. Okay, what he does is to solve the Ginzburg-Landau equations. But when you look in details, he solved in a very particular way. Inside the Ginzburg-Landau theory, he found out two equations. Here you have the ground state of the harmonic oscillator. This essentially is a particle in a magnetic field, okay? But he looked at the ground state equations for that. And once he finds the order parameter, he obtains the local magnetic field by taking psi squared and the applied field. So these equations are what I call the Abrikosov-Bogomolny equations, okay? They describe the order parameter here, with D are these derivatives in the plane, okay? And a second equation that gives you the local field. everything is translational symmetric along an axis. Okay, so these are the fundamental equations that I'm talking about. Okay, that are the most fundamental structure able to describe vortices. Okay, okay, many of you have solved the Ginzburg-Landau theory, have thought about vortices and never heard of these equations. You don't have to, but when you go and see what's the most fundamental mathematical structure behind vortices, which are topological stable structures, are exactly these equations. So these equations, they solve approximately the Ginzburg-Landau equations near the upper critical field. That's what Abrikosov solved. And what Bogomolny found in the 70s is that they solve exactly the Ginzburg-Landau equations for kappa equal to 1 over square root of 2. Okay, what I am saying here is basically the following, is that if you include the spin in this field, this parameter, so to speak, and then you take the equation that describes the psi as being this one, which in fact is the zero unicity condition, okay, and you obtain the magnetic field like this, okay, these are the equations that describe topological insulators. Notice that this equation is satisfies the divergence of the local field equal to 0 automatically. They are consistent. So my claim is that through these equations, you obtain several aspects of topological insulators, like zero energy states. People talk about, that states with zero energy. Of course, if you have this equation here, okay, I remove the magnetic field here. If you take the square of it, it's the Laplacian. So if you have a state like this, a plane wave, the Laplacian applied to it, you have that k1 squared plus k2 squared plus k3 squared is equal to 0. Okay? So these are sort of zero energy states. They explain the origin of the Rashba term. They explain the linear Dirac spectrum. They explain the topological property through the local magnetic field, not through the Berry phase. You can compute the Berry phase, but this is a more physical approach. Okay? There's a local magnetic field that surrounds the particles. And you also see the magnetic monopole nature of the carriers. So when you go and solve this equation, okay, the simplest version, what you find for a layer, let's take a layer, okay, a layer. You find out that it decays exponentially above and below the layer. So it's not really, what I'm saying is that the topological insulators are not truly two-dimensional, okay, but they evanesce away from the surface, okay, in this way, exponentially, okay, and two-dimensional, they travel along the layer, okay. So what I'm saying is that the topological insulators are kind of plasmons, okay, that travel along the surface. So we know surface plasmons are electromagnetic waves that travel on surfaces. Notice that the localization, if you take the largest momentum, Kf, say 0.5 nanometers for graphene, okay, the localization is about 0.08 nanometers, okay? So it's atomic scale localization around the layer. That's what the theory is saying. Okay, but now you go and you compute the local magnetic field, okay? There is a local magnetic associated to it. I'm not taking an applied field here for simplicity. And if you look at the structure of the wave function, okay, it flips sign, one of the components flips sign along as you go from top to bottom, okay? You find out the magnetic field, okay, component 1 and 2 parallel to the layer, also flip sign, but not the third component, which means that your magnetic field streamlines are loops like this that go from top to bottom, okay? And this is the key to the topological stability of the states. In fact, if we compute here, I will just show brief some calculations. I mean, just to give you an idea, you have these loops here, okay, like this, and you have alternating areas of positive field and negative field if you look from the top, x1, x3. So the best is to hold on to this picture. This is the structure of the quasi-particles in this theory, okay? You have magnetic field loop holes around a point, and if you look from one side of the layer, what you see is exactly a magnetic monopole. So what about the theory? Well, that's the most surprising fact, is that the theory is nothing but the kinetic energy, the Schrödinger-like kinetic energy for a spinorial field, okay? And my claim is that the Dirac linear spectrum comes out of this kinetic energy here. You don't need anything else but this. So the Dirac massless particles are in the Schrödinger massive kinetic energy. How? First thing is that you have to take this theorem, that that kinetic energy can be decomposed exactly, okay, into 3 terms. So this is just a theorem, like Pythagoras, you know. There's no other consideration. It's mathematical identity, okay? And the first term is the helicity square. The second is some kind of curvature, some kind of magnetic moment, spin interaction. And the third one is exactly the Rashba term. So what I'm saying here is that the Rashba term is inside the Schrödinger kinetic energy, something that is totally, largely ignored in the literature. Okay, so we just sit down one afternoon for half an hour, and you prove this theorem. It's not difficult. In fact, it's
Mauro, you have more 10 minutes.
Okay. So I'm about to finish. Let's see, where am I? So, of course, now I'm going to make approximations in this version of the kinetic energy. The one is that I will consider the first order equations, those ones, and then this elicited term, which is squared, will go to 0, and it will lower the kinetic energy. Okay, so there it is. It vanishes. Okay, then I have a quartic order term here, because H local field is proportional to psi conjugate psi. So this is a 4th order term. I cannot show you here because of lack of time, but that's a negligible term. And what I am left is essentially the Rashba term. Notice that it's a 3-dimensional identity there, but I can take the surface, okay, because I had a divergency, and this becomes a surface term, which is integrated in the surface of the layer, above and below, okay? So that's all that is left. And once you do all these approximations, I mean, all these considerations, the kinetic energy is just that. It is, again, here you see, is a 3-dimensional version. This is the Rashba term added to the first order equations. Okay? This is nothing but a surface term because it reduces to integration in this surface. And if I go and put my solution for the order parameter, which is exponentially the case in the 3rd direction and propagates along the plane, okay, these I have arbitrary coefficients. I found out this kinetic energy is essentially H modulus of K times this product here, and I interpret this C's as creation and annihilation operators for these quasi-particles. The solution of zero solution has a scale invariant parameter here, okay, which essentially will give me a free parameter, and I will summarize all these parameters here, including this mass, this L3, which is unknown, into the Fermi velocity, which is known to be 10 to the 6, and in fact, this free parameter is 0.02. So I cannot go into more details because of lack of time. What about topology? Topology is neither stable like a script, you know this. What's the stability here? The stability here is given by this local magnetic field that pierces the layer into twice every time. And so every point of the plane, you have a vector, which is the local magnetic field. And so I can compute this topological number, which is the Chern-Simons index, okay? I'm sure to have an integer, and in fact, I get an integer. I'm not sure the calculation here, which is, if it's integer different from 0, I have topologically stable particles that do not decay in this process of collisions and so forth. Why they are topologically stable? Because I'm taking in the plane tile, okay? In this tile, I mean, like a lattice, and I can curve the sides, and I have a cylinder, then I curve here, and I have a torus. And in each point of this torus, I have a local magnetic field. So this is the topological number, which is an integer. In fact, you compute and get an integer. So conclusion. This zero helicity theory explains the nearly zero energy of the carriers. Okay? It gives an origin for the Rashba term. It explains the presence of a linear Dirac spectrum. The topological stability is due to a local magnetic field that surrounds the carriers, okay? Which is an approach much more physical than the Berry phase. People talk about the Berry phase, like you are in a temple, talk about fire, this. Nobody understands. Here you understand the topology. You have this magnetic field that involves the particle, and you cannot destroy this arrangement, and this brings the topological stability. And if you see from one side of the layer, is a magnetic monopole of the particle. So this is all I had to say. Thank you very much for your attention.
Thank you, Mauro. We have any questions? Okay, Angel.
Recording stopped.
Voy a preguntar en portuñol. En una lámina você mostró o vector de propagación K como un número complexo. ¿Qué significado tendría el número el imaginario? Porque você tem K real y... ¿Dónde cae bien? Atenuación.
Another question, please.
I have a question concerning the physical meaning of this parameter L3, what it stands for. Yes.
When you solve this is taking there are zero incident states. Sigma V, phi equals to 0. I'm holding this equation is equal to 0. Okay? So there are scales in there. So I don't know what the scale of phi. I have three parameters here. These three parameters is the thing we need out of it. One that is in the final solution. Here. You have a scale in the margin. Part of the area in the layer, and you have a three parameters, which is the length. Together with the mass and so forth, gives us something in the scale of our velocity.
So it's a characteristic scale of the wave package.
Yes.
But why it is so that small subatomic scale?
Well,
even smaller. Yeah. Uh-huh. So if to take materials with smaller Fermi velocity, this parameter will be larger. Yeah, I see. Thank you.
Thank you, Konstantin. Now, Stuart.
Thank you for your talk. Very interesting. There are other forms of spin-orbit coupling other than Rashbar. So Rashbar is like a cross product of momentum and spin. Now, it's seen in crystals where you have inversion asymmetry and you can apply fields, and Rashbar gave us that. But if you can still see a spin-orbit effect in materials that have inversion symmetry, and the spin-orbit would be described as maybe Dresselhaus type spin-orbit, where it's more, where the kind of the energy is more like a dot product between K and spin. Would a system with Dresselhaus still go through your analysis with the kinetic energy?
Well, this is a basic analysis in the disclosure that is greater equation contains this special term. What happens with the electric field, have an additional term. This is just the most simple structure. We can see that it's there in the Schrödinger approach. Just that. I'm not saying that this will explain all the phenomena. But the only thing that I want to call your attention is the breaking of symmetry. Okay? Because when you have this magnetic field here, okay, you have a ground state with an intrinsic magnetic field. So the magnetic field breaks the time reversal symmetry. And you also break the reflection symmetry between the energy parity. So you have two symmetries that are automatically broken by this ground state. You can have monopoles and anti-monopoles circulating in a layer. You can have both. Okay? This is all the same. It's like the Ising model. The Ising model is invariant at the flicking all those things. So the ground state is up or down. Or you may give a ground state with half of the speed up and the other down with defects. So what I'm saying is this ground state of energy has related to our topology and gives you these structures that travel in the plane and break time and spatial physics. That's the structure.
Thank you. I just have one other comment. You listed all those materials where linear magnetoresistance was seen. I've looked at some of those materials, and to a certain extent, looking for topological behavior is dominated by the bulk, because topological insulators are never insulating in the bulk, and that gives you a real problem. Also, some of the manifestations of topological behavior tend to be in, say, the minority spin band, so they're very difficult to observe.
Well, I just would like to say that the bulk can have structures. And all that I'm saying is that this structure here is attached to surface behavior, to plasmon behavior, which you may have in the surface or inside, layers inside the material. That is,
Thank you.
Okay.
Thank you for your questions, Stuart. Any more questions? If not, let's thank again the speaker, Mauro Doria. The next speaker is the researcher, the Professor Paglialuso from Colombia. Okay, the next speaker is Professor Platino from Colombia. Blah, blah, blah. Okay. There was an exchange because Platino must travel, and so it will be in this moment. Platina? Yeah.
Okay, so I think it's working now.
Platina,
you.
you have 35 minutes to talk and 5 to questions, okay?
Okay.
I will advise you meeting 5 minutes.
Okay, thank you very much for the invitation for this great conference. I thank the organizers for coming here. The first time I'm in Peru, Lima. I would like to go directly to the subject. I will talk about quantum devices and at the nanoscale. I'm an assistant professor at the Universidad de los Andes, located in Bogota, Colombia. There is a picture there of the university. It's a private university. It's a very well-positioned university in the world university rankings. Currently, is in the 5th place from Latin America along the universities. And I'm also an associate editor of the Journal of Superconductivity and Novel Magnetism of Springer Nature. And so this was also an opportunity to invite you to send articles to this journal, which is increasing the impact factor. So anyway, let's go directly to the subject. Okay, so I will not have time to speak of all the topics I'm working on during these last years at Bogota. However, I would just mention briefly about the research we do over there. Also to invite students, there's one PhD position available that if you want or interested to apply, please come to me and I can give you details about the application process to the PhD. I work in it's called so-called device physics. And basically, I work on plasma resonance devices, which are looking for magnetometry applications and other related stuff. The plasma resonance devices are basically the interaction of light with matter, and also nanostructures like magnetic vortices in nanodiscs, which we have also developed at UniAndes. Second. So the last topic is the one I want to focus more for this conference, which is the quantum tunneling devices. I will talk about tunneling time, dissipation, and magnetic tunnel barriers, which has applications in spintronics. The important thing about these laboratories, when I arrived to Colombia 16 years ago, we did have in Colombia there was in UniAndes there was a lot of strong theory groups, and there was high energy physics with collaboration with the CERN, but they didn't have laboratories. And the idea was to have laboratories, but also since I was also in Cambridge, actually Anna Palou was part of the group, and in that time, I was able to notice in Cambridge that most of the techniques they were using for device fabrication were possible to implement in other places, and you have to depend so much in other institutions. So the idea was to be able to set up a laboratory so where most of the physics is done right in the location, and thanks to that, we have been able to publish papers with affiliation with UniAndes only. Of course, I'm open to collaborations, that's to say. However, the idea of these labs was to be able to do most of the work there. So what's the group? The group has been changing along the time. As, for example, in that picture, you can see two PhD students, Cesar Reño and Leonardo Rios, and my collaborator, Professor Nilima Kelkar, who is from the theory side, which we will talk about later, stuff about that. Okay, this is the Nano Devices Laboratory. I don't have time to show everything, but these two systems, we have an electron gun evaporation system on the left. That's important because that is not a commercial system that is being assembled completely at Columbia from the scratch. We have to design each of the parts of the chamber, And then we send a manufacturer, fabricate each of the parts, we put together the system, and the system is unique, understanding and mostly all the Latin, South America maybe, because it has a specific capabilities. For example, we can, well, we'll talk about the capabilities of this system during the talk. And the other one, the sputtering system, that's a commercial one, but we also do modifications. And the sputtering system is for other processes, for sputtering and co-sputtering. And here you can see one of my students disassembling the system because it's important to be able to modify things within the experiment in order to have new results. So we focus on making modifications, which normally in commercial systems you don't have a possibility. So this system has a number of capabilities that allow us to do ultra thin, ultra pure materials in the ultra high vacuum scale. So we can have reached pressures 10 to minus 9, 10 to minus 8 millibars. So that makes a good system for applications. And what we can do, we have an oxygen plasma oxidation system, ion milling for fabrication. We have atomic layer by layer growth using a quartz balance. So we can grow a rate as low as 0.2 angstroms per second. So this very extremely low growth rate allow us to make extremely uniform and extremely thin structures of different materials. For the sputtering system, on the other hand, we can control the growth with temperatures up to 850 degrees Celsius. On the superconductivity laboratory, we not only do superconductivity, we also do other subjects as well. And here you can see a magnetic optical effect built-in house. Built in the house. So for that system, of course, I had to buy some the lasers and the polarizers, but the rest have we built inside the university because we have a workshop where we can do all the small pieces that you need for a magnetic optical effect. Also, we have a commercial helium-3 system down to 500 milli-K, and the other magnetic optical effect system, there's a second one on the right, in which we can actually make measurements at the function of temperature. So I will talk about that during the talk. This is some of the results of all this work. We have actually sent up one of the devices for patenting. So it's actually patent pending process at the moment. And this device, the usage of light and plasmon resonance, you can amplify the magnetic hysteresis loops more than 7 times. So that's one of the implementations we have done, and it's currently on the patent. Okay, so I have one class that is the physics of extraordinary things for people which is not necessarily in physics. I want to start with this slide because this is the one I use for trying to explain to students what quantum tunneling is, especially if you are studying, for example, architecture. For example, you should be able to understand using this transparency. And I asked my students which ones of these heroes or basically from the comics you think has the power of quantum tunneling. So I explained to them that even though Ant-Man and the Wasp, they become very, very small, not necessarily they have quantum tunneling powers. However, there's a villain, the Ghost, which is able to, apparently based on comic description, phase through matter and become invisible. So phase through, in a sense, is tunneling going across the matter. So that's why it's quantum tunneling about in the simple explanation. However, I will tell you during this talk, hopefully you learn how actually quantum tunneling is made experimentally beyond the textbooks. So here we are going to talk about these devices, quantum tunneling devices, which has a cross function. And also I will include magnetic materials to do spintronics. So that's what I will talk about. The requirement to do quantum tunneling devices that I have learned along the time with people I have talked all over the world is that you have to have very high quality tunnel junctions with superior growth and fabrication parameters. This is necessary because otherwise quantum tunneling is very difficult to obtain if you don't have those qualities. So what we're going to do is the research is going to strip down all the tunneling junctions in order to understand from way to the bottom all the details about quantum tunneling, and then we keep increasing the number of layers and difficulties from there. So let me show you. Okay, these are my collaborators, which have helped develop measurements of determination of tunneling characteristics and dwell times. Dwell times, as we will see, is tunneling times. And without their help, it's not possible to do this job. So what I will talk about during this talk, what is quantum tunneling or why it's important in solid state physics. That is, we'll talk about some preliminary work. Then I will go on to how to make tunnel junctions, characteristics, how long does it take? That's also another question we will address, how long the tunneling time takes in order an electron to cross a barrier, how much energy is lost, and we will talk about quantum friction, and how does an electron spin tunnels across the barrier. The last point is important because we add an additional degree of freedom in which we include the spin, not only the charge of the electrons. So what's quantum tunneling? I tell my students, if you have a package, if you want to some time in the macroscopic world, you basically have to pay the energy, which is the mass times gravity times altitude to the height of the mountain in order to have the package going across. And you really have to get to do that. In quantum tunneling, in quantum world, this actually you don't have to do. You can send the package across the mountain, and you can actually get without paying all the price of the energy. But the difference that you only have a probability for this to happen. There is a character in a famous coffee shop, Juan Valdez in Colombia, and this character is a man with his donkey. And I was telling them, well, if he lived in a quantum world, there is a finite probability for Juan Valdez to go across the mountain without going up all over the hill. So that's what I represent there in that cartoon, right? This is the classical way that they explain quantum tunneling where we are in undergraduate physics, but never tell you the details. They never tell you in the class, or maybe some classes do. Well, I tell them now, but it's how to make this in actual experiment, and how if this is actually something real that we can actually use in experiments or not. So I'm going to talk about that, and there are some applications already in quantum tunneling, but we don't have a quantum tunneling devices in computers or things like that that work very well. People are working on making device quantum tunneling junctions, but we have some applications already. For example, in the superconducting quantum computing, we have tunneling devices there. We have also magnetic tunnel junctions that serve as the head of the hard drives that can work also for applications. Still in the process of getting into to industry. Then we have a tunneling microscope on the top down, and this tunneling microscope already can produce very nice images of vortex, images of vortices, and even graphene has been used to make a tunneling barrier. But also I put this transparency because just to show you that I do have some stuff related directly with superconductivity. And for the people who are interested, you can look it up this paper where quantum tunneling is studied when Cooper pairs behave as bosonic particles with respect from the experimental point of view. And also, there is also this other article where it's actually superconductor ferromagnet spin valve structures, where we can actually flip or control the vortices of the structure. No? So that's just two articles for you if you guys are interested to go into that. I will not talk about that, but I will. Anyways, how to make a solid state junction in real life? Actually, it's not something that people completely control. It would seem like something people understand, but for example, there are simulations, very recent simulations on how to optimize the fabrication process of aluminum oxide tunnel junctions. So the basic process, the basic idea is you have a metal layer, metal contact, then you put oxidize it with oxygen plasma, then you get a very thin layer of oxide that is around 2 nanometers, very uniform, and then you have the metal oxide on top. And that would be the basic tunnel junction. There is others that you can do, but this one's the basic architecture, but you have to put also, as you will see, silicon oxide on top. And there are some properties like the barrier height. I don't see. Like the barrier height, wait a second, okay. Like the barrier height that changes with temperature. So we grow these tunnel junctions, and here you can see the cross of the tunnel junction. Well, the important thing about this device is that all of this is made in situ into the device, into the e-beam evaporation system. This device comes nothing, you put everything in the substrate, and then you fabricate everything inside. And you do this through shadow mask. So you put shadow mask, and you can be able to produce this nice tunnel junctions. You have to put also silicon oxide here to isolate these two parts. So there's a number of additional stuff that basically you need. And the measurements are 4-point measurements. You send current and measure voltage here, okay, on the right, top right. Send current, measure voltage, and thus you get the IV characteristic, current voltage characteristic. We do the measurements in this system that plays with temperatures between 3 and 300 K approximately. And the important thing of this system is that I can not only do transport measurements, but also optical measurements. So if you have samples which you would like to measure optically and by transport at the same time, we can do it here. These are the results. In order to know if you have a tunnel junction, the IV characteristic has to be curved like that. And also, there is something that gives a strong temperature dependence that is changing with temperature between 3.5 and 300 K. Important information here is that it works at room temperature. That's also important, these devices, that they can function well at room temperature. And normally, we tell the students, go down in temperature so that you don't damage your device, but we realize that that's not necessarily true all the time. So here on the right, you have the results on resistance versus temperature. And let me show you here. You have the fit with the theory and the experiment. Here you have the famous Simons model, how it fits the theory with the experimental results. The fitting is very well. And the important part of this is that you have to get the barrier width. So this is the tunnel. Okay, this is actually important. You get the barrier width, or how thick is this barrier, and the barrier height. Okay, that's the important result that you will get from this data. Okay, and that will help us to explain what's going to happen later. So here, when you do that, you can see that the barrier height is increasing when you lower the temperature. So this barrier height is increasing, okay? One thing I have to just remind you quickly, where is this? That in our case, the thickness of the barrier is the thickness of the oxide layer, about 20 angstroms, 2 nanometers. And the barrier height is 1.8 electron volts, okay, or 2 electron volts, depends. So you can have also the phonon frequency you can get from these measurements. You can get a lot of information from there. The second question, how much time do I have, Luis?
Sorry?
How much time?
You have 10 minutes more.
Okay. The important first question we want to address is that how much time it takes for an electron to go across a tunnel junction, right? So if you ask people, they think, or I used to think myself too, that the time it takes is 0, right? That the tunneling process across the barrier should be 0, right? But it turns out that it's not the case. There is people have been trying to do experiments to measure in the tunneling time. There are some examples there, 2012, 2008, and 2001. And the tunneling times they get is 1 times 10 to the minus 15 or 1 times 10 to the minus 18, the attosecond scale. So extremely, as you can imagine, these extremely small times are so that we don't have a clock in order to be able to measure such small times. So we do it through extrapolation with the theory. We do that. We take the theory, we take our data, and we extrapolate, and we x times 10 to the minus 16 seconds at mid-barrier energies. So contrary to what people know, that was the first time we extrapolated tunneling time from actually solid-state tunnel junctions, because these other tunneling times are not from junctions, are other systems which do quantum tunneling, but not tunnel junctions. So we got that. We are quite happy because it's basically near the order of what people, but actually this is more exact measurement because the other ones are just approximate measurements, are not exact at all, because it's impossible to have a measurement, direct measurement of tunneling time. Anyways, I will continue. If you want to read more about this, there's a paper on that. And I will go on with quantum friction. Quantum friction is how much energy is lost. It turns out that when we were making tunnel junctions, since I was in my postdoc, a lot of tunnel junctions all die very easily, right? So they are very sensitive to current. So if you put too much current, it breaks down and burns out. So I told my student, this really makes me happy because I want to make these robust tunnel junctions. Let's investigate dissipation of energy in tunnel junctions. So we did this investigation. And this is very important also for applications as memory devices, because you want, when you make memories with tunnel junctions, you want them not to dissipate so much heat. So there has been like a few people trying to do this friction, quantum friction, and there's one quote from this paper from Tommaso, where it says the quantum effects on friction being largely unexplored. We show here that even a basic theoretical model predicts important novelties. So there is not so much on quantum friction. And the question is how effective or not is measuring technique in preventing the tunnel junction. So if we can understand quantum friction, then we can, the way we send the current can be modified in order to have less dissipation, right? Or less heat, and also be able to dissipate this, thermalize this heat with the bath. So also, can we establish a maximum voltage threshold we should not pass? And this was basically, what are the maximum voltages we can use for this tunnel junction? So we devised an experiment in which we should not direct current flow, but pulses of current, pulses of electrons that go across the tunnel junction of the order of 20 milliseconds, and check the IV characteristic. And this was the result. You can see that the red is the pulse current, and the blue line is the DC current, direct DC current. So actually, this was surprising because we expected for the pulse current, you send pulses of current, you have time to cool down your tunnel junction, and still you get lower voltages and lower currents. What you see over there is the breakdown, the destruction of the tunnel junction when you increase voltages. By the way, normally people don't get to those voltages because they don't want to break their devices, and it's very difficult to have the quality to do that. But so we were able to go all the way to the highest voltages possible, and it turned out that the DC direct current method had larger currents, extremely large, as you can see, that got through there. We were devising a model to study dissipation, which is not included in the Simon's classical model for tunneling. We devised this model, we published a paper on that, and the important part to explain here is that when you look up to the data, and then you try to fit a model with Simon's model breaks down at high voltages. So it works very well at low voltages, but high voltages break down. And that's related with how energy is dissipated in tunnel junctions. The model essentially includes the velocity of the particles and a gamma parameter of dissipation of junction. So we did that. Also, it's been investigated by Gabelli also, that when the voltages exceeds 1 volt, the tunnel junction emits infrared radiation. So it's not only heat, but also radiation at certain voltages. So that's important also to take into consideration. With the results on dissipation, we are still analyzing, but essentially you have here the fraction of energy that is dissipated, and contrary to intuition, it actually goes down as temperature increases. So yeah, of course, if you increase the temperature, you have a larger thermal energy. However, the dissipation, the fraction of energy, percentage of energy that dissipates is lower. Okay, this is also another important result. I will just mention that resistivity or resistance of the junction as a function of voltage, you can see from the DC pulse method, there is like a drop in the resistance near, it's not superconducting. However, the conductivity increases dramatically at high voltages for that junction, okay? What's the explanation? Basically, the barrier height is an important parameter. So if the barrier height is a little bit smaller, then the dissipation is smaller. That was the main conclusion. Let me finish with how does electron spin tunnels across the barrier. This is important because it's the last result we have. And here, what we do is we include a magnetic layer, and we talk about not a magnetic tunnel junction, not a ferroelectric tunnel junction, but something different with this magnetic barrier junction. We modify the properties of the barrier. Okay, the magnetic barrier junctions can be changed if you put in magnetic impurities. You notice here that there is an X, because I cannot tell you which impurities we put there, because there is actually a possibility we are analyzing if it's a possibility to patent this process. So they told me at the transfer office at the university, you cannot disclose this information. However, I tell you these are magnetic vacancies that we put there. So we do that. This is the result. When we put the magnetic impurities, we get a magnetic response, but it's not just any response, it's a super paramagnetic signal of the magnetic properties. And it's important because it's a thin film solid state material. So it's not, we don't have nanoparticles. We have a solid film, and that's why it's important to have superparamagnetic signal of that material. We do that. We start applying. Remember that we change temperature. In this case, we start applying magnetic field, and then we see a clear dependence on the IV characteristic of magnetic field, which is a very good result. We were very happy. We're still analyzing this information, this data. I just can tell you what happened. Probably the internet. Basically I was finished, but essentially the barrier height can be controlled with magnetic field. And that's basically the main result we are having in this junction. Thank you very much.
Thank you, Edgar Platino, for your excellent talk. And now is questions. Mauro. Sorry, Mauro.
Usted tiene un ejemplo de la barrera. ¿Qué material puede ser la barrera?
La barrera de potencial the barrier material can be aluminum 203, aluminum oxide. But the trick is make it extremely thin and uniform.
Thanks for the question, Mauro. Mauro, the microphone.
About the time that electron needs to cross the barrier.
Yes.
I mean, can you do interference measurements? I mean, some, say, a beam that does not pass through a barrier and the other that passes through a barrier, and through interference determine the time that takes, the time spent on the barrier.
The problem is that it's in the attosecond scale, and there is no electronics that you can do such small frequencies existing in this planet. So no, the short answer is no, it's not possible to make direct. The question is, can you make direct measurements? No, we don't have a clock to even for interference, which is a good idea, right? But it's still the time period so small that we don't have electronics.
Okay. Thank you.
Konstantin.
Thank you for your interesting talk. I have a question related to the term which you called quantum friction.
Yes.
If I understood correctly, you consider not elastic tunneling.
Exactly, yes.
Where the final energy differs from the initial energy. Then the question is, what is the source of energy dissipation?
When we investigate dissipation, we basically do not say a specific source. We say whatever the dissipation is, we measure that dissipation. But the source of dissipation is could be through infrared radiation, that I already told you, above 1.2 volts infrared radiation, and the other one heating, local heating. But how this?
But local heating of what? Where?
The electrons interact with the barrier below the barrier height. So within the barrier, they interact, and it's strange because it's a good question. What do you interact? Maybe with phonons?
Okay, but if we make a barrier just a vacuum.
If it's okay, so if it's just in vacuum where there is no barrier,
yes,
then the infrared radiation.
And is it measurable? This photon emission.
People have not done those experiments, but it's a good idea actually to try to do those. You do that with noise measurements. Start measuring noise measurements, but infrared, yes, you should be able to measure infrared even with those experiments. But people have not done it yet.
I see. Thank you.
You're welcome.
Any more questions? No? I have a question. What do you think that missing in the Simon theory to fit above 1.2 volts?
Simon, when we proposed his theory, he did not consider dissipation. So when you try to fit above 1.2 volts, you just basically cannot.
And so in this region, there is this dissipation so much.
Yes, so we include a term. We use the Simons model, but we add additional term, and that's how we feed it, and then we get a nice fit, and we get dissipation. In the time of Simons, even today, you cannot, when you look at a conference, notice that the currents that they send through a tunnel barrier is basically in the order of microamps. And we get to the milliamp scale. So we really send really, really high currents because people don't do that because they break down the junction that they cannot work with that anymore.
Okay, thank you. Any more questions? No. So thanks again, Professor Edgardo. And any comments?
And now we will have a break. Then we can continue the next talk later. Okay, let's go to the break.
Hi, hi. Hello, hello. So welcome back after the tea break. So I welcome Professor Stuart Holmes from University College London. So he'll be talking about transition to mini body localizations in GESM devices. So it would be a wonderful talk and ask many questions. He can answer patiently. So he, of course, he's an old friend of mine. I know him since more than 10, 12 years. So, so welcome back, and Stuart.
Thank you, thank you, Pratap. I'll start my wonderful talk now. Okay. Thank you again, everybody. Thank you to the organizers. This is my second talk at this conference. Again, it's not really, it's an orthogonal direction to magnetism and spintronics, but never mind. So I want to tell you today about some work, some fairly recent work. Some of it's ongoing. I'll tell you where we are with the research. It's a part of a nationally funded, EPSRC-funded program with many partners. I'm just going to tell you about my contribution. I'll list all the partners at the end, but I'll just tell you about my contribution to this particular field. So it's looking at germanium tin devices, and germanium tin is a strange material. Now, I've spent most of my research career in industry, and when you're in industry, you always think, well, what's the product? Why are we doing this? How much money are we going to make from everything? But it turns out germanium tin is quite useful because germanium, as we know, is a semiconductor, and it's nearly a direct band gap, but it's not. It's not a direct band gap. If you strain it or add tin to it, it becomes a direct band gap. So that then opens the whole field of optics and photonics to a silicon platform. So it's very attractive to industry. However, what is not known is that when you put tin into germanium, you create all sorts of problems like localization of charge. So I'll talk about that. So talk contents, introduction to the material, and also what is many-body localization. I'll talk about electrical transport measurements. I'll talk about some of the localization and a summary at the end. Okay. Again, I made this rather grand series of quotes, say, in the abstract, some of which are true, some of which are speculative. But the take-home message is that really nature abhors the metallic state in germanium tin. That is your take-home message. No matter how sophisticated the measurements may seem, we're still stuck with this fact that nature has given us. Okay, so in the introduction, I will tell you about some of the experimental issues of trying to study many-body localization, in particular the importance of disorder, and then I'll move on to the germanium tin devices themselves, how they're grown and so on, what their basic properties are. So many-body localization has been with us now for many, many years, as has localization. I mean, when we first started looking at semiconductor devices, semiconductor materials, most of them were disordered anyway. They weren't grown in a very clear way. They had unintentional doping. They had defects. When we made a heterostructure, there was, again, defects and impurities which stopped the devices working in the way that we wanted. However, we're re-looking at this field, and what we're trying to do is we're trying to take away, when we make a device, imagine this system here is our semiconductor device. We're trying to take away the link to a thermal bath. So we're trying to create a system that's disordered, And in a disordered system, we characterize the kind of the transport properties by hopping. So the charge just hops through either impurity sites or some other sites, hops through the lattice by hopping, and that's thermally assisted. Question is, if we take away the thermal bath, so there are now no phonons in the system, what do we get? What can we characterize that system? What do we get? Does the system form a many-body localized system? So, experimental considerations, thermal isolation, that involves a lot of time in the clean room, but it's great because we're trying to make these, essentially, we're starting with a 2D material, and we're trying to take away some of the layers in the structure to form things like nano bridges, or bridges, not really a nano bridge. The scale bar here is 2 microns. So this is an image of it's a hole bar, so it's a 2D system. We've etched away underneath the hole bar. So these, you can see where we've etched underneath here, and we get these completely freestanding structures. Now, not in germanium tin, but this is actually in gallium arsenide. We can do that in gallium arsenide. We're trying to do that in germanium tin. And what we do here is we nominally take away the way that the lattice can vibrate. We can't take away all the phonon modes. There is a zero energy phonon mode. We can take away most of the phonon modes. Why is disorder important? Disorder is important because that gives us this hopping conduction mechanism, which is, as I've said, thermally assisted. These measurements are done at low temperatures. The energy scale is quite low. We have to be around 1 Kelvin. So the interesting transport measurements are all around 1 Kelvin for this. There's a reference there, Nankishore and Hughes, 2015. They did a kind of a review of the field. And the field of many-body localization is really not semiconductors, but it's other things like cold trapped atoms and things like that. The low temperatures, this is a picture of a helium. This is a picture of a helium-3 probe that I renovated when I first started working at UCL. I renovated this probe. What we're also doing is introducing disorder by ion beam damage. And if you saw my talk on Monday, you would see some of the structures that we're able to make at high dose levels. At low dose levels, we can introduce disorder, and it's quite good because we don't lose carrier density, we just increase disorder, so we lose mobility. The charges lose their mobility to move, but we don't lose charges. So those are the basic ingredients that we need to consider. So a little bit more detail of the transport properties themselves. Now, when we do our undergraduate lectures, we think of a Drude conductivity. The charge in the system is characterized by a carrier density, a charge E, an elastic scattering time tau, and an effective mass. So the carriers move through the system with an effective mass and a scattering time, and you combine those numbers together, you get the conductivity. So you apply a voltage, you measure a current, the current is determined by the conductivity. All very, very simple. The carriers diffuse through the system. What happens if you put disorder in? If you put disorder in, here is a plot of the density of states as we go up in energy. EC is, let's go back. Mu is the chemical potential, so that's where we're doped to in the band. So this band of carriers is doped to the chemical potential here. And when we have disorder, we have something called a mobility edge, so that all states in the density of states above the mobility edge, this blue area here, they conduct. All states below this, they are localized and don't conduct, okay? Now, the interesting fact here is that we can change the chemical potential with gating, so we can use a gate, we change that chemical potential. We can change this energy between the chemical potential and the mobility edge. And if you measure the conductivity in the system, the conductivity is thermally activated. Okay, the conductivity is thermally activated. Simple exponential, and the characteristic energy is the energy between the chemical potential and the mobility edge. What happens as we reduce the chemical potential deeper into the band is that the transport mechanism can go over to hopping. So the charge now no longer, well, when we have a mobility edge, we can still get diffusion. So we get kind of a thermal excitation to the mobility edge, and the carriers have a lifetime. They can diffuse at the mobility edge with a particular lifetime. When we reduce the chemical potential, we can have the possibility of hopping now. And we've still got this temperature dependence of the conductivity, T0. T0 is a kind of the energy gap between the mobility edge and the chemical potential and the mobility edge. But we've got this extra power here, P. Obviously, for this mobility edge, P is just 1 here. When we've got this phonon-assisted hopping, this exponential power here, P, changes. And depending on the type of hopping, it can be MOT. If it's MOT, variable range hopping, in 2 dimensions, the power here would be 1/3. And there's a second type of hopping called Efroshklovsky, which is slightly more sophisticated. When the electron hops, or the hole hops, it leaves a hole, or the electron would leave a hole, and it gets bound to that hole. But it has a slightly different energy because it's bound to that hole. So it kind of creates like an excitonic state, and that shifts the energy of the system. So when we're in this hopping regime, what is interesting is that this prefactor to the conductivity here is E²/h. So it's just the quantum of conductance, but the system is thermally assisted. How does it know that it's got this fundamental electronic conductance when it's thermally assisted? So what we're trying to do is we take away the thermal bath. What have we got left that can help the hopping mechanism? So one of the mechanisms that's left is Nyquist noise. The question is, does this Nyquist noise lead to a non-ergodic behavior? Do we have a new state of matter? What we also see in this, what's also predicted in this many-body localized state is that the thermal conductivity goes to 0 as well. So the thermal conductivity goes to 0, and the conductance goes to 0 at non-zero temperature. So that's roughly where we are with the many-body localized. That's that. And then this is the introduction to the germanium tin devices. They're grown by reduced pressure CVD. We collaborate with the University of Warwick, which is near the city of Birmingham, quite near the city of Birmingham in England. They are grown on silicon, so the basic substrate is silicon. And then they grow germanium layers, they put doping in, they put spacers. The germanium tin itself is confined to just 15 nanometers of the quantum well. So when we put germanium in, that reduces the band gap. This forms a quantum well, and then we cap the layer. So this figure here is a kind of a solution of what the bands are. So we've got the valence band here. So this is distance through the structure. This is the surface up here. This is the energy of the system. The 0 energy here is a chemical potential. Chemical potential is in the valence band. So this is the valence band. This is the conduction band, which if we look, if we look in K-space, this is the K-space representation of the band structure. We've got this direct band gap at the gamma point. We've got the L minimum, and we've got the heavy hole states. These layers are strained, so we've removed the degeneracy between the light and the heavy hole states. If we were to put more tin into this structure, the tin percentage here is about 9%. If we would put more tin in this structure, the gamma point would come down with respect to the L minimum and form a direct band gap system. Okay. What we find in our devices is that they are p-type, so the chemical potential is down in the valence band. So this is what the structure looks like. It's a kind of a redrawing of this structure. And what happens in this system is we've got this tin quantum well here, and the tin is such a large atom that it tends to surface segregate. So it tends to surface segregate towards the surface as it's growing and forms a disordered layer. The tin forms a complex with a vacancy, which is a hole trap. So we can trap holes here at this interface. So that's where we get this disorder from. That's the nature of this, of the problem in the system. If you get the growth totally wrong, the tin sits on the surface and forms beta tin, which is a superconductor. So if you get the growth wrong, you can actually see tin on the surface. Interestingly enough, we've still got this high level of disorder. And the first measurements that we did, we cooled it down in the cryostat. I think this is 1.5 Kelvin. We cooled the device down in the cryostat, applied a magnetic field. So this is actually almost the raw data. This is just the voltage drop along the device, so proportional to the resistivity as a function of magnetic field. We see a very, very clear magneto-oscillation. If you work out what the mobility is, it's a few hundred. It's about 380 centimeters squared per volt second. If you look at the quality of these quantum oscillations, I mean, we see spin splitting. We see some kind of weak anti-localization, possibly some geometric magnetoresistance, the spin splitting. So it's all very, very high quality magnetoresistance. If we Fourier transform this data, so these dotted lines here just show the kind of the field domain. If we Fourier transform that, these, as I mentioned on Monday, these oscillations are periodic in 1 over field. So if we plot the Fourier transform of this data as a function of fundamental field, we see extremely sharp lines in the Fourier transform. And as I mentioned on Monday, we can determine the quantum lifetime or quantum mobility or single particle lifetime from this data just from the width of this peak. This is a harmonic here, so this is at twice the frequency. This is due to Zeeman splitting. So we've got a Zeeman, you can see the peaks here very, very, very clearly split by the Zeeman effect, okay? But if we look at the fundamental field, measure the half width, we get this huge quantum mobility, 37,000 quantum mobility, which is extremely unusual. Usually the mobility, the classical mobility is usually a lot larger than the quantum mobility. So we've got a very unusual system here. Okay, so moving on to some of the gated devices. So ungated devices, then gated, and then the high magnetic field data. If we look at this is very, very simple data. This is mobility as a function of 1 over temperature. So this is high temperature up here. This is also the conductance as a function of 1 over temperature. So this is high temperature up here. High temperature is maybe 10 Kelvin point. So that would be 0.1 on this scale is, I think, we start at 10 Kelvin and cool it down. There's a bit of a gap in the data where we have to transfer it to a different cryostat. So this is going into that helium-3 system that I showed you at the start. What we find is that the mobility is thermally activated with the same characteristic energy as the conductivity. It's this excitation to a mobility edge. If we measure the Hall effect, which we've done to determine the mobility, the Hall effect is constant. There's no change in the carrier density. There's no activation of the carrier density in this system. We move on to the gated devices. So to make the gated devices, we put down a layer of aluminium oxide, a little bit thicker than we heard earlier. It's about 40 to 60 nanometers. And we can apply something like plus minus 20 volts approximately. So this data here is the conductivity, the device conductivity as a function of carrier density. This carrier density is changed with the gate voltage. So this is 0 gate voltage up here. As we apply a positive gate voltage, this is as I said, is a hole gas. So if we apply a positive gate voltage, we decrease the hole density, okay? So this is at higher temperatures. We see this activated conductivity. We also see this extremely sharp drop-off below about 1.5 10 to the 11. So this is all happening at fairly high carrier densities. As we reduce the temperature, we increase that. So the slope here changes. We're increasing that distance between the chemical potential and the mobility edge. So as we increase that energy difference, we see a much stronger activated conductance. There are other effects going on in here. You can see this noise. That is not experimental noise, it's real noise. As I say, we also see this extremely sharp drop-off, which I'll come to in a few minutes. What we would have also liked to have done is to measure the Hall effect in this region. But when you start to get very, very resistive materials, so we're starting to get the resistivity now, if you measure the resistivity, it's something like 10 times the quantum resistance. So they're going up to hundreds of kilo ohms to mega ohms, which are very, very difficult to measure in these systems. So, as I said, we've got this activated mobility. This is a slightly different set of data. This is a device conductance now as a function of 1/T. It's a different measurement to what I showed before, but you can see it's nicely activated. And then this data here is where we get this sudden drop in the conductance. It's still activated, it's still thermally activated, but we think what's happening here is we're opening up a gap in the density of states. Okay, I'll come on to that. We're still in this thermally activated conductivity region. Just to put some of the numbers in, this activation, this characteristic temperature T0 is about 5 Kelvin. So that's the thermal energy between the mobility edge and the chemical potential, which is about 0.4 MeV. Okay, so it's all low temperatures. To see an activated conductivity here, we'd have to be significantly below 5 Kelvin. Okay. We published some of this data last year. That's the same set of data. Yeah, we published some of this data. What we also did as we were doing that work was we took some of the samples to Grenoble, where there's a high field magnet lab, where we had 32 Tesla at our disposal. So the question was, what happens at high fields? And interestingly enough, this is now resistivity, so ρxx as a function of magnetic field. We were going up to 30 Tesla, but the device, we're measuring, that's 10 to the 6 ohms per square, 10 to the 7 ohms per square. And the device was about 10 squares. So we're measuring extremely high resistances here. But what you can see is, once we get those carriers to that mobility edge, you can see a very, very clear Shubnikov-de-Haas effect. And we see a very, very clear quantum Hall effect. I haven't plotted the quantum Hall effect. It's still there, but it's getting swamped by this very, very high resistance. So amazingly enough, we have this localization behavior. Once we get the carriers to the mobility edge, we can see very, very clear magneto-oscillations. What's also interesting is if we plot the resistivity as a function of 1/T at fixed field now, it's a slightly awkward plot. But they extrapolate down to this sigma 0. Sigma 0 is the minimum metallic conductivity. So we see this very, very clear minimum metallic conductivity in the system. What we'd like to do is go beyond that, go into the hopping regime. So we're really looking for this hopping regime in this material. We're hitting it with low carrier densities through the gate. We're hitting it with high magnetic fields. Okay. A little bit more on the localization. Tell you a little bit more about the mobility edge. And then I'll come on to the more recent measurements. I'm trying to study this in one dimension, so I'll show you some of the devices, some of the behavior that we see in one dimension. We also see this stochastic. We also see the behavior that is not many-body localization. We see virtually every other behavior, but we haven't seen many-body localization. So this is this. Apologies, I've shown this data many, many times now, but this is device conductance as a function of gate voltage. This is another set of data. So this is depleting the system. We're doing this at constant temperature. So this is 10 millikelvin. This is in a fridge now, 10 millikelvin. This is 1 Kelvin here. This is 10 millikelvin down here. So you can see it's very, very clear activation of the conductivity. I've also plotted the same data now as a function of carrier density. We see this very, very clear transition at this point. For this particular data, we totally lost the conductance, whether we've lost the contacts or the system just, well, it would be nice if the system collapsed into a many-body localized state, but I don't think it does. Interestingly enough, what we also see in this data when we apply a magnetic field, we see this so this is what I'm plotting on this false color plot now is magnetic field as a function of gate voltage. And you can see when you plot the data in this fashion, you can still see the Landau level structure coming out of there, even though we're deep in this localized regime. So from the fits, if we fit, we've got lots of data on this. If we fit the conductivity now, the temperature dependence of the conductivity, we extract two parameters, sigma naught, the prefactor, and T0, this, well, KB, the Boltzmann constant, times T0 would be the activation energy. All I've done now is I've just plotted from all the different fits, see lots of data fits here, lots of data sets here. I've plotted them all out. And if you plot them all out, sigma 0, this is plotting sigma 0 now in units of E squared over H as a function of T0. Okay, so that's the activation energy, T0. They all sit on a universal curve. And it was quite striking initially. What happens is this prefactor comes down and just gets anchored at this point. It's about 0.78 E squared over H. Okay, it's very, very clear in this system. If you look in the literature, you just say, well, oh, it's just Mott's minimum metallic conductivity. Mott predicts this 0.1 of E squared over H bar for this behavior. Very, very clear in this device. The carrier densities involved here were about 4 10 to the 11 at this point, 1.6 10 to the 11 down here. So at this point, it doesn't go over to hopping. We get this. Well, there's several things that could be happening here. We think there's possibly a gap in the density of state. If there's a gap in the density of states, it looks like an Efrosh-Shklovsky hopping mechanism, because this introduction of this exotonic state gives you a band gap that is linear in density of states that's linear in energy. But what we don't get is we don't get the temperature dependence of the conductivity, which would indicate that it's hopping. So just to kind of summarize this set of data that I've showed you, I'll just remind you we've got this confinement for holes in this system. It's very, very clearly got a mobility edge. Okay, it's all thermally activated, but there's no hopping. So we've got this a kind of a false color plot here. This area of low temperatures and low carrier densities. So this is kind of carrier density in units of 10 to the 11. This is temperature in Kelvin. This side we've got a metal. At low temperatures, the conductivity doesn't go to 0. We've got this thermally activated conductivity. We've got this dotted red line here, which shows us where the system comes down to this minimum metallic conductivity predicted by Mott. So at the minimum metallic conductivity, the elastic mean free path can't be shorter than the distance between the atoms in the lattice. So that's originally where it came from. Also, sigma tends to 0 down here. Once we've gone through this region, this conductivity tends to 0. So that's one of the signatures that we're looking for with this many-body localization state, but it hasn't come through this hopping conductivity. We also get some other details. Sometimes the conductivity increases. Sometimes the conductivity increases as we're decreasing the temperature. So this property is negative. d sigma by dt is negative. D sigma by dt goes to 0. So at some of these regions, not very much happens. Okay. So just to summarize this, we get this. Well, I've called it a metal insulator transition, but it's already in the kind of localized insulating regime. If we look at the interaction parameter. So the question is it interaction or is it disorder? Is it disorder in the lattice or is it carriers that are interacting? If we look at the interaction parameter, it's really quite small, 1.5. This interaction parameter is just 1.5, so it's really disorder. We haven't really got interaction in the system. What we've also done is we've managed to suppress this inelastic scattering, this non-hopping behavior. There's no variable range hopping down to 100 millikelvin. Okay. Now, there is a theory. We've got the University of Birmingham working on this. They've produced a theory for what's potentially what's happening here. Okay, so moving on to the 1D. Okay, thank you. I should have talked about the 1D first, I think, but never mind. This is an image of a typical device. We've got a source and drain contact. These can be quite far apart. The source and drain can be several hundred microns apart. The important bit about the device is the split gate. So these are surface gates that are split by exactly 400 nanometers. So this is an SEM image. We've got split gate 1, split gate 2. We also have a top gate, and we produce this top gate. We call it a midline gate. So it's done at the same level of lithography as the split gates. So the operation of the gates, the split gates change the width of the channel. So we've got the channel width is the channel is horizontal. The top gate changes the carrier density. When we define a 1D channel, it's just a 1D channel under the top gate. Okay. We cool the system down. It's maybe not so surprising that the conductance is actually rather low. This is microsiemens here now. So the quantum of conductance E squared over H, 2E squared over H if we've got spin, is at 77 microsiemens. So we're well into this disordered regime. And we just think, well, we've got Coulomb blockade here. Okay, we'll come back to that. We've got, if we plot out the conductance, so this conductance here is at 0 split gate voltage. So it's just the 2D conductance, which is thermally activated. Question is, once we form a 1D system, do we still have that thermal activation, same thermal activation? So this is plotting the device conductance as a function of split gate voltage, where we reduce the carrier density by putting a depleting voltage on the midline gate. As we put a depleting voltage on the midline gate, well, we've got Coulomb blockade in there, but we've got a real mess. And people again would say, that Stuart Holmes person, he doesn't know how to do measurements. This is all just noise. But if we replot this set of data in a more systematic way, so what I've plotted now is I've plotted the device conductance on the y-axis. It's on a log scale, just to kind of expand what's going on at low signal levels, as a function of the conductance at 0 midline gate voltage. So the first set of data will be just a straight line. That straight line. As we apply a midline gate voltage, we see very, very clear Coulomb blockade oscillations here. So we've got this condition for Coulomb blockade, which means the current can only change, the current through the system can only change when it meets the condition for a Coulomb blockade. And it's very, very clear in this system where this occurs. It's also a stochastic system. It's also stochastic. We know it's going to change the conductance when we get the condition for the Coulomb blockade through the system, but we can't predict exactly what it will be. We can predict when it will be, but we can't say what it will be. So the system is going over to percolation. It turns out the system is kind of going over to a percolation through a series of random quantum dots. And we can confirm that by applying a DC voltage. If you apply a DC voltage, so that's applying a DC voltage along the channel between the source and the drain. And if you plot that out as a false color plot, so this is device conductance plotted as a function of split gate voltage, and the y-axis is DC voltage from 0 to 1 millivolt and 0 to -1 millivolt. And we see here kind of the Coulomb diamonds. We see Coulomb diamonds. They're not quite quantum dot Coulomb diamonds because the system is very, very well connected to the source and drain regions of the device. But nevertheless, we can see that we have a charging energy here of 0.4, something like 0.4 MeV. So the system goes over to a series of random quantum dots. So just in summary, I've told you about the effects of disorder. I've told you about some 1D behavior. The fact that in these disordered systems, we don't get this many body localized states. We get something that's a result of the inhomogeneous behavior of these systems. Future devices suspended. I wanted to talk about those. I'll just quickly mention, this was my latest attempt to make a suspended device, and you can see it's kind of clearly failed here. So this is a silicon germanium quantum well device that's kind of failed because I haven't etched it properly. So I'll have to come back and explain the data when I get the processing properly sorted on that. And those are my collaborators. I'll stop there.
So questions, please.
Thank you for a nice talk. I just have a quick question about the Coulomb blockade device, the last one. You say that was stochastic, right? So let's remove the noise for a second. Just imagine we remove the noise. You have clear steps, right? So how is that stochastic? In which point will become stochastic if you just remove the noise?
It's not noise. It's all totally reproducible. If I sweep the gate box, there's no noise there. It's all reproducible. It's all signal.
Okay,
there's no noise.
This stochastic process occurs with between the steps?
So once we've determined where Coulomb blockade occurs, when we apply it, when we reduce the chemical potential, we know where the Coulomb blockade will occur again, but we don't know what the conductance will be at that point.
And you sit there and you see stochastic.
Yeah.
All right.
It's definitely stochastic, but it's not stochastic in time. It's fixed in time. It's stochastic when we change the top gate voltage. There's no noise in that system.
Okay. And can you make it stochastic in time or not?
That would be nice, because if it is stochastic in time, then it's possibly a chaotic system. And what I'd like to be able to do is show that it's a chaotic system and study that. That would be a nice...
Yeah, it has applications to quantum computing.
But it would have to be time dependent. Yeah.
All right.
And at the moment, it's not time dependent.
Okay. Yeah. Thank you.
Thank you for the interesting talk. I have a question about this pre-exponent sigma 0. Is there some special meaning why in your case it's appeared smaller than conductivity quantum? Somewhere it was shown that it is 0.12 H over E.
Yeah, so Mott's theory was just a theory. So it actually comes down to roughly his value. Is that the plot that you were worried about? It is Mott's value, effectively. The fact that it's 0.02 parts in 0.1 is not a problem. The problem with data is it doesn't go over to hopping. If you look at a silicon MOSFET, it would go over to hopping. So we're not seeing that hopping behavior. So somehow we've suppressed this inelastic scattering in the system. Did I answer your question? Was your question the disparity
yes.
between the theoretical values?
I naively might imagine that sigma 0 should be always E squared divided by H.
Yes, once you're in the hopping regime. Yes. Yeah, once you're in the hopping regime. And it's also different between Eppler-Shklovsky and Mott. There's a factor of 2 difference between the two. Yes, I agree. But we never got into that inelastic scattering regime.
Thank you.
Last question, please.
regime.
Yes. So we have. So this step left here. The station on the left. We know we're at the mobility edge. We're coming up from the minimum metallic conductivity, but we can characterize this resistivity here by a diffusive system. But once we get the carriers to the mobility edge, they seem to behave as a normal diffusive system. So you can characterize this. We get the carrier density. We've got nu equals 1 here. We can calculate the carrier density. It's about 2.9 times 10 to the 11. Very, very clear magneto oscillations. We can kind of, from the Hall effect, which is beginning to get distorted, we can get the mobility. Mobility is just a few hundred. So we can get mobility and carrier density. So we can get scattering time and effective mass, plus this activated conductivity. So once you get the carriers to the mobility edge, they seem to diffuse around at the mobility edge and give us this nice quantum oscillations.
But I mean, if it has a good behavior, could you characterize it as a metallic regime?
That's a good question. It's probably not metallic because it has a gap. But that's where my understanding stops, I'm afraid.
Thank you.
Thank you for your talk. Why do you say that these systems are non-ergodic?
So when the system is non-ergodic, that's in the fully many-body localized regime. And if you look at a small part of the system, say some dependence of a small part of the system, it doesn't represent the full system. It just represents a small part of the system. But when it goes into this many-body localized regime, it just remembers what it had previously. Energy can't diffuse, charge can't diffuse through the system. So it means that a particular part of the system is not representative of the full whole of the 2D system. It kind of breaks up into non-ergodic behavior. Sorry, does that answer your question? Sorry.
You say it's a matter of size at the end.
Yes, size is important, yeah. So if you measure, usually when you measure a device, you measure macroscopic size contacts. They all agree. If you take away inhomogeneities, they all agree. With the many-body localized state, they don't agree. They don't agree.
Okay, thank you.
Yeah.
So that was a wonderful talk, Stuart. Due to time constraints, we can't take any more questions. The speaker is available. Let's congratulate the speaker. So next one is a lecture. So the topic is plasma deposition of superconducting and magnetic thin films. So it's part 1 of the lecture. Magnetic target distance effect on low vacuum magneton spectrum. So it's the speaker is M. Villamay from Central Mindanao University from Philippines. So she came a long way. She took 2 days journey. So let's appreciate her. So is it ready?
So while they're setting up, I'll just give a short introduction about myself. I'm Michelle Villamayor from the Philippines. I finished my PhD in 2014 and conducted 6 years of postdoc in 3 different universities. So I did my first postdoc in Linköping University, my second postdoc in Grenoble at Institut NEL, And then my third postdoc at Uppsala University, also in Sweden. So Linköping and Uppsala are both in Sweden. Then I had 1 year industry experience in chromogenics, where we do roll-to-roll sputtering of electrochromic thin films. Last year, I decided to come home to the Philippines, to my province, and be closer to my family, to my parents. So they're getting older, so it would be nice to spend more time with them. And I can hear my voice. To do my PhD also in the Philippines and partly in Doshisha, Japan as well. So finally, my talk is going to be shown in 5, 4, 3, 2, 1, 1/2, 1/4, 1/8, 1/16. There you go, 0. All right, so as I mentioned earlier, plasma deposition of superconducting and magnetic thin films. This is a lecture series. This is one of 2 today. So I'll be presenting today and also another one tomorrow. So this is in collaboration with Professor Valladares and also Professor Aguiar. And we have started this collaboration in February this year when I was invited as an online speaker during the LAFMAT conference. Next slide, please. So I actually traveled a long way. First, I traveled from Mindanao, which is a southern island of the Philippines, and then from Metro Manila, I moved to Taiwan, 4 hours, then to Los Angeles for 12 hours, slept over in Los Angeles, and then woke up early in the morning at 6 a.m., then came to Peru from 12 noon, and then arrived here around 8 in the evening. And luckily, Professor Maria Luisa Saron was able to pick me up from the airport. So what is Central Mindanao University? So the Philippines is actually composed of 3 island groups. We have Luzon here, we have Visayas over here, and we have Mindanao. That's why my university is called Central Mindanao University, and it's in Maramag, Bukidnon, Philippines. So a few information about the country. It's an archipelagic country. We have 7,641 islands, but every year it's increasing because we have better and better camera technology. There's a 109 million population in 2020, and we have more than 120 languages. But don't worry, I don't speak 120 languages. I only speak 3 when I was growing up. In the Philippines, we had the earliest occupants around 709,000 years ago, based on recent results in terms of history. And we were under the Spanish colonial rule in 1565 to 1899. When Spain decided to sell the Philippines to the USA, it became a neo-colony of United States. And during the World War II, it became the war zone between Japan and the USA. And this eventually started to shift the language from Spanish, which was the official language, to English. So right now, we are learning actually the national language, Filipino, and also English. Because in 1987, the Constitution was ratified and they changed the official language from Spanish to English. So this is Mindanao. I actually live here. I grew up here. We call it Land of the Mountain People, or in Bukidnon. This is the Bukidnon capital, and we have an annual traditional festival called Kaamulan Festival. Okay, so about Central Mindanao University, it was founded in 1910, predominantly as an agricultural university. This year, we had more than 16,000 student enrollees, and we own and operate 3,080 hectares of land. So just to give you an idea, 1 hectare is 10,000 square meters. We have 9 colleges, and the BS Physics program started in 2013, which is predominantly aligned to material science. So this is our graduating batch. They are finishing in 2024. As you can see, the gender divide is quite strong. We only have 4 boys, and we have 7 girls for this year's graduating batch. In our faculty, it's actually 50-50. There's 6 girls and there's 6 boys, and the chairperson is a woman, and that is me. And for the next batch, it's a little more lopsided towards the boys. We have a few girls, but still it's not 2 girls out of 20, but there's actually 1, 2, 3, 4, 5, 6, and 7 and 8, I think, out of 22 students. There's more batches, but it's mostly roughly the same, equal number. So I guess I'm very proud of saying that we are doing good in terms of gender equality in the Philippines. So now let's move on to plasma. Now, what is plasma? It's composed of, it's actually solid, liquid, gas, and plasma and it's a 4th state of matter. And more than 99% of the visible, take note, visible universe is made up of plasma. So the naturally occurring plasmas are the stars, the sun, the nebulae, and also the auroras. We can actually create commercial plasmas, and these are obviously neon lights, fluorescent lamps, and also the plasma TV. Neon lights are so called because there's neon inside these vacuum tubes. Using a sign transformer, we could actually create atmospheric plasmas. The high power and also the gas inlet. We let this air pass through this high voltage wires, tungsten electrode wires, and then the air plasma gets activated and creates a plasma jet. But of course, we can replace these tungsten electrodes with other types of metals. Now, moving on, physical vapor deposition is actually a vacuum technique. So permanent magnets are strategically placed to increase the sputtering rate of the target material. But I will talk about that in a short while. So low vacuum, we are talking about 10-1 to 10-2 torr. High vacuum is 10-3 to 10 to the -7 torr, while ultra high vacuum is from 10 to the -8 to 10 to the -11 torr. This happens, low vacuum is if you're just going to use a rotary pump. High vacuum is if you're going to use another pump called the turbomolecular pump. It's actually composed of rotors and stators. So these are alternating blades. Every other layer is moving, and the next layer is actually static. And it helps bring out the gas from inside. Let's say this is the chamber. From this part of the chamber, it helps put away the gas outside and it gets pumped out. So that is how pumping happens for high vacuum. Now, if you would like to have ultra high vacuum, you would like to heat up the entire chamber and also pump down for a few hours to up to a few days. So this is how a magnetron sputtering works. We have a metal target, and then we have magnets underneath the metal target. What happens is that there's going to be a confinement. Now, if we introduce argon gas into the system and then create a bias between the metal target and the grounding, for example, we would activate argon to become argon ions. And then the electrons get trapped in the magnetic field, thereby the argon ions attacks the metal target. If we do this for a long time, then we get to harvest the metal target and it gets deposited onto our substrate. Sometimes these metals will get deposited on the side of the chamber. So that's how magnetron sputtering works. So what are the applications of magnetron sputtering? As I mentioned earlier, I was working with roll-to-roll sputtering. We were able to deposit on glass, polymer, and then this polymer is actually sandwiched to create we put an electrolyte in the middle, and then these two polymers are deposited with indium tin oxide and nickel oxide, and the other one is indium tin oxide and tungsten oxide. In between that is an electrolyte, and then these things get sandwiched in between the glass. This glass becomes our window. Now, what's the difference between this window and this window? This one is switched off, and this one is switched on. Now, this is how the electrochromic window works. And it was a startup company some 20 years ago, and now it's a commercial company. Some of you have seen this before, but this is the roll-to-roll sputtering system bought from Germany, transported by land to Sweden, and then it was introduced into the factory because the building was already built and the door was too small, so they had to create a hole on top of the roof so this machine can go into the building. So this is the size of the machine, and these were two of our working students. They were doing their masters in Uppsala University, and these guys, our full-time workers, trying to align the substrate, which are a few kilometers long. So this is our polymer substrate. Okay. So this is the cut through of that machine. We have the intake roller, the payout roller. It has to go through a lot of these tension rollers. It goes through the drum. The magnets are here, and there's 1, 2, 3, 4, 5, 6 chambers where we can deposit different types of material. It opens through the substrate drum and also through the target. Okay. So this is the size of the machine. It's 18.20 meters and it weighs 130 tons. So it's much more heavier than all of us. This is almost the size of this room, actually. So this is how the magnets are positioned inside the target. So the target is actually a cylinder, and then you have magnets which is oppositely facing different. There's 3 sets of magnets. The middle one is oppositely facing so that there's going to be a confinement in the middle. And if we would like to change the target, let's say from nickel to tungsten, we have to take away the magnet and then replace it with another target. And to do that, we need actually a couple of guys to move the set of large magnets. And we have to be careful not to be bringing our cellular phones because it's going to destroy our phones. So I hope it plays, but it seems like, unfortunately, it's not, the video is not playing. There you go. So it takes a couple of strong guys to move the magnet out of the target. and into the other target. Okay, so this one is actually what it looks like on the side. This is a target, and this target is showing some plasma, and this plasma is actually reflected onto the drum, and this drum actually has a polymer layer surrounding it. Okay, so the drum has to be very smooth, otherwise the polymer will have scratches and it's gonna be disastrous for our final material if there's going to be damages onto our polymer film. So the next machine I'm going to show is actually the first plasma devices in the Philippines. It was made up of an all-glass chamber. This is around 1989. This is Professor Ramos. He's the one who introduced plasma physics in the Philippines. And he was also my professor when I was a bachelor, master's, and PhD student. The power supply at the back is actually a machine that the Japanese university was throwing out, and he asked if he can have it and sent to the Philippines. So eventually we were able to patent it, and it was improved to become an all-metal chamber used for commercialization. And these are some of the few samples that I worked on titanium nitride. This is the machine. It has Helmholtz coils used for plasma confinement. So when we turn this on, the plasma becomes a sheet-like plasma instead of a circular one. And this one is another sputtering device. It's quite small. It's the size of a hamburger. This was developed in Japan as part of my PhD, and we were able to deposit zinc oxide, transparent conducting oxides, using this machine. And if the parameters are wrong, then instead of depositing something transparent, then we will have a zinc foil, which looks exactly like this. Okay. Sometimes, if we input too much power, we would destroy the zinc and we would create a hole on top of the zinc material. So actually, this is very small. We can bring it anywhere. This one is the product of my research studies in Japan. I went home to the Philippines, brought the technology, and made my own during my PhD, and this was my ticket for my PhD graduation. We were able to deposit antibacterial titanium dioxide. So these are the samples that we tested. It's just that we deposited the TiO2 on the glass, and then we dipped the glass on the bacteria, and then the dipped glass was placed onto this krypton soya agar plate. And if there was no TiO2, then the agar plate is full of bacteria, whereas those with titanium dioxide actually inhibited the growth of bacteria. And this one was done during my postdoc in Uppsala University, where we deposited a single layer of tungsten disulfide onto this 4-inch silicon wafer. The reason that we say it's single layer is because we have seen a photoluminescence of this material, and we also tried a Raman mapping where we monitor the distance of the A1G and E2G peaks, and from here in this gray zone is actually covering this values here. So we have this single layer of our material. And now moving on to Mindanao, we tried to replicate the things that we have done in Manila, which is the capital, to a province where we mostly don't have these advanced materials at all. I was lucky enough to have a student who's very hardworking. We bought this small pump, single stage pump, and we have this hobby kit to create resin materials. And we modified to create a magnetron sputtering system. However, the pump is too small, the chamber is too large. We had actually problems of igniting the plasma. Other than that, we didn't have a working power supply. But luckily, there were those in the area who knew how to build their own power supply, and they built one for us. It's some 2 hours by bus away from where I was working. And then I instructed him, okay, you can build one for me and then give it to someone in the bus. And then we will pick it up in the bus terminal. And he actually disagreed on doing that because this item looks like a improvised bomb. So we didn't transport it by bus, but someone picked it up from their university. So meanwhile, we were also preparing to create this atmospheric plasma. Some items were shipped from Manila, and we wanted to build this in the Philippines. Now we were able to ignite our plasma sources.
I think everybody is waiting for the tour. Can you please wind it off in 5 minutes?
Sorry?
So 5 more minutes, please.
Okay, 5 more minutes. So these are the applications: thin film deposition for the low vacuum plasma, and surface modification for the atmospheric plasma. But there are limitations for low vacuum. So we have inferior quality thin films. Oxide contamination cannot be avoided. We have arcing, and most of the time we had power supply damage. For the atmospheric plasma, it is small area. The process is either too slow or too fast for some processes. We need to work on high voltage, so we have to be careful when it comes to handling and the high contamination content due to the atmospheric nature. So with that, I will just stop for now and continue the presentation tomorrow. Thank you very much.
So that's a wonderful talk. Any questions, please? We'll take some questions. Is everybody interested in tour only? You don't want to ask questions?
I think they're hungry for lunch.
There is a speaker over there.
Thank you for the talk. I understand the difficulty that you have because it's difficult to start a lab from the scratch. Congratulations.
Thank you very much.
These windows that you presented at the initial part, you were saying that you can switch. Can you explain a little bit more the windows that you have different layers?
Okay. So I could just go back to that slide. It will be easier. Yeah, so first, what we need to do is to deposit just one part. So this is the polymer, then deposit ITO, and then deposit nickel oxide. So that's one part, okay? So that's one run. And then we do another run on another polymer. So we deposit ITO and then another layer of tungsten oxide. So that's another run. And then we have to create a system where they can be sandwiched together using an electrolyte. So there are already systems for that. The chromogenics company has actually 2 factories, one for sputtering, and the other one is for the laminating. So we are mostly in charge in the deposition of the thin film of ITO and nickel oxide, and for the ITO and tungsten oxide. After that, the product is out of our hands. It's moved on to the lamination factory. The lamination factory is in charge of creating a sandwich, putting the electrolyte, and also creating this glass polymer polyester sandwich and glass. So, and also creating this large windows.
And this company is where?
This is in Uppsala, Sweden.
Okay.
So you can check them out. They have a website for this one.
All right, thank you.
You're welcome.
Any more questions?
If no questions, I need to give a strong announcement.
Thank you.
Thank you very much. Thank you very much. Well, before we finish the session, I need to give some announcement, very important announcement. Those people who are going to participate in the tour now, because it is not short of time, 12:50 is past bring Flores. And in Miraflores, you will have some time as well. If you can get something around here until 12:50. If not time, we are going to give you a lunch box. Don't worry, and you can bring with you during your eating that. And in Miraflores, you will have just some minutes as well because they are going to. And you will need to board another bus in Miraflores in Larcomar. That bus, they will guide to you to many places.